This next section, 10.2, is on the gravitational field. And we want to discuss what we mean by a field. You've heard in science fiction about a force field and things like Star Trek of people being caught in force fields, or people being in jails that have force fields that are invisible as a door, which look kind of imaginary. But a force field is really a redundant expression because a field is a force that's exerted on an object. We define the gravitational field. By definition, as the force that's exerted on a unit mass. And the gravitational field is a vector. So if we want to know what the gravitational field is, say right here on this desk, at this particular point, then all we have to do is to put a mass here, measure the force, and divide by that mass. It's easier just to put a 1 kilogram mass here. So if we put a 1 kilogram mass right here and look and see which direction that force is in, then that force divided by that 1 will be the gravitational field. So the gravitational field points downward. And you can see from this that near the surface of the Earth, since F is equal to mg, that when we divide that by m, we simply get g. So the vector g, the acceleration due to gravity, is in fact the same as the gravitational field. So if someone asks you on a test, what is the gravitational field near the surface of the Earth? The answer is 10, or 9.8, or 32 feet per second. Or you could say it's equal to the gravitational acceleration anywhere, on any planet, and so forth. And the reason that it's equal to acceleration, and that's not only true, that's only true for the gravitational field, not for the electric field or others. That's because we divide the force by the mass which is affected by that force. So it is a force per unit mass. Now having that, once you have the field, you can multiply by the mass and get the force back again. So if somebody says the gravitational field is 30 at some point, and that's the gravitational field, then they say, what is the force that a 2 kilogram mass would experience in that field? And the answer is the force would be the mass times the gravitational field, or 2 times 30, which is 60. 60 what? Newtons. I know that can be confusing, so you need to think about that just a little bit. Remember, the gravitational field is defined by the force on a mass that would be at a given point. And the fact that it's identical to the gravitational acceleration can be a little bit confusing. Now, we wrote out that force a while ago as we had the expression up at the top that F 1 onto 2 was equal to the negative of G M1 M2 divided by R2 minus R1 quantity squared times R2 minus R1. I believe that's, yes. Divided by the magnitude of R2 minus R1. This gives us a unit vector in the correct direction. Now you notice this minus sign here really inverts this, so this is the force of 1 on 2. We can make this a plus sign and write this as 1 on 2. And since this is a magnitude, they become 1 on 2 also. So we could rewrite this as G M1 M2 over R1 minus R2 squared. And since that's the magnitude, we don't have any trouble. It's the square of that length. So it's the same whether it's R2 minus R1 or R1 minus R2. Both vectors has the same length. Divided by R1 minus R2, magnitude, again the same argument. And that minus sign inverts these, so it's R1 minus R2. That's the force that 1 experiences on 2. And so we can from that, look at what a small mass would do to a large mass and look at the gravitational field. How might we do that? We would say, well, let's look at the gravitational field from some large mass. So we put G, small m, large M, and let's just call this R squared, the distance between them, over R1 minus R2. And let's put this large mass at the origin. So we're going to put a coordinate system here, put our large mass M at the origin. So we have a vector that goes to the large mass, and the large mass is going to be 2. The small mass out here is going to be R1. Let's do that backwards because we want to look at the force that is exerted on 2. So we call this mass 1. So here's our mass. Our big mass is R1. Our small mass is R2. And so we want to rewrite this as that's the force that 1 exerts on 2. So that is the force that 1 exerts on 2. What direction is it going to be? Well, it's going to be the force that 1 exerts on 2 is going to be 1 minus 2, but R1 is 0 because we've got this mass at the origin. So therefore it turns out to be, and this is a unit vector, it's divided by R to give it a unit length. So it's actually going to be back in this direction, minus R2. And sure enough, that is the direction of the gravitational field due to this force. So we do have the signs right for that unit vector. And that's what we've written out basically up here. Now if we have many masses, and that's the expression we write up here, the gravitational force due to many masses, let's say a whole set of masses I focused on some mass M is going to be G M sum over Mi times Ri minus R divided by Ri minus R cubed. Now why do we say cubed? Well, we could have used that cube all along. Here we have the square of a term and the first power, so if we multiply these together, we get the third power. One of those powers is simply to make this into a unit vector. So the force that exists on this one mass is going to be the sum over all of these masses of Ri minus R. This is what we'd experience here on the Earth. We would experience the force due to all of the planets, the moon, stars, even the asteroids, maybe even other parts of the galaxy to some small extent. And therefore the gravitational field would be the same expression divided by m. In other words, without this m present. And that's the way we calculate the gravitational field at a point, is by adding up all their masses times the vector Ri for the position of that, and how far it is away from the location of that one mass or the position, divided by Ri minus R cubed. Again, that third power is just to cancel the length of this and make it into a unit vector. Okay, let's review that very quickly and say again, what is a gravitational field? Gravitational field is the force per unit mass. The force near the surface of the Earth is mg, divided by the mass, m, and we get g. So simply stated, the way to think about it is the acceleration due to gravity at some place is the gravitational field. And therefore, if you think about the Earth here, gravitational field is always pointing inward. And if you had two objects like the Earth and the Moon, it points inward to the Moon also. And so actually, if you look at the way the gravitational field is shaped, it's not a perfect drawing here. It'd be coming in here to the Earth, like this, coming into the moon like this, kind of like if you look at two like poles of magnetism, where the electric field lines are either pointed away or towards the two magnetic poles, as we'll discuss later. So you can kind of see what that gravitational field will be like. Remember, the gravitational field always points into the object because gravitation is always attractive. We don't really know of any object that has a negative mass, although for a while in the 1950s it was considered a possibility that maybe antimatter would have a negative mass. A negative mass would give us anti-gravity. It would fall upward. Because of this equation here, if one of these masses were negative, the force would reverse its sign and they would be forced apart. Well, it turned out that after those measurements were made on what are called antineutrons, the antimatter for neutrons, it was found that they do fall downward in a gravitational field. So even matter, to the best of our knowledge, falls in a gravitational field and therefore has a positive mass, although it can be shown to have a negative energy. We'll talk about that more when we talk about relativity. The key thing here is this force per unit mass. Now I want to talk just a little bit more here about what we mean by a field, because we're going to be encountering a field over and over again as we talk about the electric field and the magnetic field. So let's say, what do we mean by a field? This is a more of a philosophical kind of concept. And this is how it originated. Originated also with electricity and magnetism as well as gravitation. Let's say we have two objects. Here's the Earth, and here's the Sun. As we know, there's a pull between the two, so that the Earth is pulled toward the Sun and the Sun is pulled toward the Earth. By Newton's third law, every force has an equal and opposite force. But now this is a vacuum. And so it bothered people that somehow or another these objects could reach across nothingness and pull on something else. You see people's experience where things like, if I had a rope and I attached the rope or the chain to this object, or we had a mass that stuck out here and I could pull on part of the mass, or reach my hand out there and pull on it, that would be different. How do I pull across a vacuum? If it's truly a vacuum in outer space, then there's nothing there. If there's nothing there, no force could go between them. This was really a riddle to the people at the time when gravitation, and then especially electricity and magnetism, were being studied. And they said, well, here's what they finally came up with. Every object, like the Earth and the Sun, that has gravity, exerts a gravitational field. So if we just look at the Sun by itself, there's a gravitational field that pulls into the Sun. The point here is, if there's no Earth at all, there's still this gravitational field. The gravitational field, G, is a condition in space. And they say, okay, here's the Sun, and it causes a condition in space that does something to the space. It makes a gravitational field. Then if we put the Earth in that gravitational field, it feels a pull. So what they did was they separated in this force, F is equal to G, mass of the Earth, mass of the Sun, over the radius squared. They said, let's separate this and write mass of the Earth times G ms over r squared, and call this the gravitational field of the Sun where the Earth is. In other words, the force per unit mass of the Earth divided by the mass of the Earth gives you G mass of the Sun over r squared. And therefore they said, let's call this the gravitational field. And therefore, the force that something experiences is the mass it has times the gravitational field. And sure enough, all they've done is factor this expression into something they call the gravitational field and the mass that finds itself in that field. So you can say, well, that's just playing with mathematics. It turns out that that's not true, because you can ask yourself the question, is this gravitational field real? And is the electric field real? And is the magnetic field real? And although this is hard to prove for gravitation, we can prove this for electricity. We are looking for gravitational waves. And so if we took the sun and shook it, or better yet, let's take a 1 kilogram object and let's shake it back and forth, then since it has a gravitational field that comes in, and since no effect can go faster than the speed of light, this gravitational field, as it goes out, will experience wiggles. And these wiggles will constitute a wave that should travel at the speed of light. Well, that's very hard to measure because gravitation is so weak. But what we can do is we could get an electrically charged object. I always like to take something that wakes people up in class. Let's take a cat. We're going to take this cat, this furry cat, and we're going to rub its back and make this cat electrically charged. Then we're going to slightly shake him, not enough to hurt him. And as we do, you can see that there's going to be an electric field. It turns out if it's a positive charge, the electric field goes outward like this. And so when we shake this cat, we'll produce wiggles in this field. Do these wiggles exist? Are they real or are they not? Well, the way to test it is you take the cat, charge him up, shake him a little bit, then neutralize him so he doesn't have any positive charge on him. Now he's neutral. And now that he's neutral, does this wave oscillate out here through space? And the answer is, if you have another charged particle Q out here, sure enough, this charge will feel that. And this thing right here is called an electromagnetic wave. In other words, it's light. Or a radio wave or microwave or some form of electromagnetic radiation. So this is real. Therefore, the field is real. And the oscillations in those fields are real. And therefore, we are confident that the gravitational field is also real. So it's just an interesting kind of psychology that led people to talk about the field. And remember, you can talk about the field of an object even though you don't have the second mass there. So force exists between two objects, but the field exists if there's just one object. The field comes into that object.